Hello, I am Yasunori Toshimitsu from the University of Tokyo, and I will present my research, Biomimetic Operational Space Control for Musculoskeletal Humanoid Optimizing Across Muscle Activation and Joint Null Space. First, let me talk about musculoskeletal robots. These type of robots have a passive joint structure and contractile actuators emulating muscles. These robots have a biomimetic design, and since they are modeled after animals and humans which can move very efficiently, it is expected that the research of these robots will lead to more capable robots. Also, since these robots have such a human mimetic structure, they can be considered as a human body simulator platform and can be used as a platform to understand biological motor control. This work focuses on operational space control. This type of control tries to achieve the actual task in operational space, such as the hand position and orientation, rather than the joint pose. It's demonstrated here, where I try to keep the coffee cup steady in space while moving around. Here is the same task executed by the musculoskeletal robot arm. Even when the arm is pushed, it tries to keep the coffee cup in the same position and orientation while compliantly reacting to the external force. This uses a biomimetic muscle model to optimize muscle activations. The same movement can be expressed differently in separate spaces. Tasks are often described in operational space, using hand position or orientation. The joint space describes the joint angle pose of the robot. For musculoskeletal robots, the actual control commands are sent in muscle space, with parameters such as muscle length and muscle tension. Therefore, we can consider that controlling these musculoskeletal robots can be described as converting from operational space tasks to muscle space commands. During this conversion, there are two redundancies that must be resolved at the joint and muscle level. When converting from hand position to joint pose, the joint redundancy must be resolved. Here, different joint pose can achieve the same hand pose. Therefore, we must determine how to choose the appropriate joint pose. Next, when converting from joint space to muscle space, the muscle redundancy must be resolved. Here, infinite combinations of muscle tensions can generate the same joint torque. So we must think about how to control this muscle coactivation. Both of these redundancies must be resolved in order to control musculoskeletal robots. Here I compared the proposed approach and the conventional approach to resolving these redundancies. Conventionally, two separate controllers are used to control musculoskeletal robots. The first controller converts from operational space to joint space and can be a controller for conventional axis-driven robots. An inverse kinematics calculation is one example. Then, a joint muscle mapping that is specific to musculoskeletal robots converts from joint space to muscle space. On the other hand, in the proposed method, these two redundancies are resolved in a single step using the operational space controller. Next, I will talk about the biomimetic muscle model that we have used in the controller. Here, we consider the hill-type muscle model. This model is commonly used to describe the macroscopic muscle behaviors. In this research, a simplified force-length relationship was used, which approximates the actual biological muscle's force-length curve using a second-degree polynomial. Muscle tension F is comprised of active and passive elements, and the muscle activation A, which is the control input. The active element Fa indicates that muscles can output higher tension near the optimal length, and is described with the red curve in this graph. The passive element Fp acts like a nonlinear spring to limit each muscle's motion range. Thus, we can consider that this model states that the muscle is easier to move when it is near the center of the motion range. Next, I will talk about the dynamics of musculoskeletal robots and how we can apply it to operational space control. First, I'll talk about conventional axis-driven robot dynamics. For these robots, the dynamics can be described with the standard manipulator equation. M being the mass matrix, C being Coriolis and centripetal force, and G is the gravity compensation torque. The differential relationship between the hand position x and joint angle q can be described with the Jacobian matrix J. In conventional operational space control for axis-driven robots, defining the mass matrix in operational space M bar is the key to converting between operational space and joint space. This is the control law required to achieve the reference acceleration xr in operational space. Here, tau no is the no space torque, which can take any value without affecting the operational space acceleration. Next, let's look at how to describe the dynamics of musculoskeletal robots. The relationship between the muscle length L and the joint angle Q can be described with the muscle Jacobian Jm. The muscle Jacobian Jm can also be used to describe the force-based relationship between the joint torque tau and muscle tension F, as in this equation. Thus, this equation describes the relation between muscle tension and joint torque. When you consider converting between these two values, F and tau, calculating the joint torque from muscle tension is easy. It is simply a matrix calculation described with this equation. However, the other way around, calculating the muscle tension from joint torque, is not straightforward because of the muscle redundancy. Even in this minimal example, you can see that there is an infinite combination of muscle tension which can generate the same joint torque because of the redundancy. Thus, this is often formulated as an optimization problem that satisfies this equation. An objective function that is often used is the squared sum of muscle tension. So what is an appropriate objective function for musculoskeletal systems? In this research, we chose the squared sum of muscle activation A as the objective function. Thus, the operational space controller for musculoskeletal robots can be formulated as a quadratic optimization problem described here. The muscle activation A and the torque null space tau no is the optimization variable. The objective is to minimize the muscle activation and null space torque while fulfilling the dynamics so that the robot can achieve the reference acceleration in operational space. The resulting muscle activation value A can be considered to be the most efficient activations to achieve the desired acceleration in operational space. Here's the system diagram of the proposed Hill model-based operational space controller. The desired task is given as the position, velocity, and acceleration of the operational space. This is converted to a reference acceleration value using a PD controller, as shown here. Then, from the actual robot, the kinematic and dynamic parameters, the muscle Jacobian, and the biomimetic muscle model, active and passive elements, are computed and is given to the quadratic optimization. The muscle activations are converted back to the muscle tension command and then sent to the robot. Next, I will talk about how we implemented it on the physical musculoskeletal robot and then the experiments we have conducted with the proposed controller. We have used the musculoskeletal humanoid arm platform Musashi L arm in this research. This arm is tendon-driven, with a brushless DC motor pulling a Dyneema rope. In each of these motor units, there is a load cell to measure tension. Thus, it is possible to conduct muscle stiffness control or muscle tension control with these motors. In addition, this robot is particular that it has a modularized joint mechanism. In each of these joints, there is a potentiometer that can measure the joint angle. Thus, the real-time joint pose of the robot is obtainable. In all, 7 joints and 15 muscles were used in these experiments. For this experiment, we have measured the compliant response of the robot to external disturbances. The task was to maintain this constant hand position. The elbow position was pushed inwards 4 centimeters using a force gauge. The hand position deviation, delta x, was measured, along with the force required to sustain the elbow displacement. For comparison, we have run the same experiment using joint stiffness control. As the elbow is pushed, you can see that the hand position deviation increases to 4 centimeters, and also there is a constant external force required to sustain the elbow displacement. On the other hand, for the proposed operational space controller, even as the elbow is pushed, the hand position deviation does not increase that much. Also, the external force gradually lowers to 0 again. From this, we can say that the operational space controller reacts compliantly to the disturbances while retaining the hand position task. In this next experiment, we show that the robot can follow the same dynamic trajectory using different arm poses. The white dot indicates the desired trajectory, and the RGB axes indicate the end effector pose. You can see that the robot follows the same operational space task even while the pose is modified. In this experiment, we have measured the effect of including the torque null space in the optimization. The arm was released from a high elbow pose that requires a high muscle activation to keep it in place. When the null space was included in the optimization, the arm can gradually drift to a pose that uses less muscle activation. And you can see here that the muscle activation value gradually decreases over time. However, for this experiment, where the null space was not included, the elements marked with the orange box was not included in the optimization. You can see that the muscle activation value does not decrease over time. Thus, we can say that the proposed method can exploit the joint torque null space in order to gradually lower the muscle activation and drift to a lower elbow pose. We've also developed a UI in order to control the robot more easily. By moving this green sphere around, you can control the end effector position of the robot. For the final demo, we show that the operational space controller can work even for an extended end effector position. Here it tries to maintain the same position for the badminton racket tip. In conclusion, we have applied a operational space controller to a musculoskeletal robot arm. It uses a biomimetic hill-type muscle model in order to model the force-length relationship of the muscle. Also, it incorporates the torque null space into the optimization process. As a result, it can utilize both the joint and muscle redundancies to achieve tasks while being compliant to external disturbances. Thank you for listening.